So this could be called 4.1 Part B. There is a reason these two are separated out. They work a little differently than the other ones that we did worked. We're looking at more historical numeration systems here. So just as in the ancient numeration systems, they evolved to meet practical needs, they often carried spiritual significance, reflecting beliefs about the cosmos and divine order. Many cultures saw numbers not just as abstract symbols, but as expressions of a deeper sacred reality. And we'll actually see that in at least one of the systems in this section. This intertwining of faith in God and mathematics reminds us that our search for knowledge and meaning has always been connected, blending logic with our search to make sense of the world. So the system that we're going to look at first is the Babylonians. And the Babylonians only have two symbols. They have a symbol for the value 1 and a symbol for the value 10. Their symbol for the value 1 looks like an arrow, kind of like an arrowhead. When I draw them on here, I'm going to warn you, I will draw them like a less than sign. Okay? I'm drawing a partial symbol. And their number 10 looks like a triangle, what we would probably describe as an upside down triangle, although triangles don't really have direction. And when I draw mine, I will draw it not filled in. Okay? Now, obviously, you can't just have two symbols and get away with that, because if I need the number, 78, it's probably not even that enough. I've already got lots of symbols I'm going to have to draw to do 78 if I just do repetition of symbols, right? I would. I'd have quite a few. And what if I had, 1,078? What would I do then? Okay, so it's not just repetition of symbols. So what they have is they repeat symbols if their values are less than 60. Okay, if it's less than 60. And then they actually have a positional base 60 system. So we have a base 10 system, right? The ones place, the tens place, the 10 squared, which is 100, 10 cubed, which is 1,000, and so forth. They do the same thing, but they do it with 60s. So they have the ones place, and then they have the 60s place, and then 60 squared, and 60 cubed, and so on. This not having a 0 is going to come back to bite us really bad in this section. Babylonians not having a 0 is a big problem, because there's not one. I don't know why they would not have a 0. You'll see with the Mayans in a moment that they have a 0 and they still end up with some problems. But kind of like our leading idea talked about too, David, right? This idea of numbers and senses, right? They evolved over time, right? This need for something arises and then we change the structure of something. I think there's definitely good reason why this is not the system that we still have today. You'll see lots of good reasons, but the 0 being a really big one of them. Okay, ready to try? Oh. Okay, so I'm going to draw my not so nice symbols to give us some ones to work on. You see some stacking going on in their system. Again, stack, don't stack, it doesn't really matter, but you'll see them do both inside of my math lab. These are the ones we're going to do. By the way, this is when your calculators are going to come into play, not on this one, on the next one. This system, but the next set of problems. No, I think you're going to need them on this set of problems too, actually. I take that back. Okay. So for starters, let's just identify, kind of like we did before, what the values are and where the place values are. Now, I mentioned when we were doing Chinese, right, they put their symbol and then they put the tens value underneath it. So like they put, a 9 and then they put 100, right? They didn't put the 100 on top of the 9. Okay, so, and we talked about the Romans where the smaller value coming before the larger one changed the meaning, right? So with the Babylonians, they always put the bigger symbol before the smaller symbol. So right here, when we have a smaller symbol, the triangle turning into the bigger symbol, the less than sign, that breaks the place value. It has to. The bigger values can come before smaller values, but you can't have smaller values before bigger values within the place value. So anytime you see triangle, arrow, the place value changes. So let's, for just practice, notice down here too. Do you see any places where it goes triangle, arrow? I have arrows, triangles, arrows. So right here is going to break place value. I've got arrows, triangles, that's okay. And then I've got an arrow again, so it's going to break place value right here. Did I get it right? Yep. Anytime you see a triangle in front of an arrow, that's a 1 in front of a 10, it's going to break place value. Okay, is everybody okay? For starters, that's the system's property. Like that's how they set it up. So within that, you see repeated symbols that we are going to add together. So we have 2 of the arrows, and then we have 1 of the triangles. What is 2 arrows and a triangle put together if you just count them up? 21, okay? So this right here is 21. We'll talk about what we're going to do with the 21 in a moment, but it's 21 if we just counted it. How about 2 arrows and 2 triangles? 22. Okay, everybody good so far? Triangles are worth 1, and the arrows are worth 10. Did I write it backwards on the other slide? Did I really? I did write it backwards. I'm so sorry. Let's flip them. No wonder I'm getting some faces when I'm doing things. This one's triangle, this one's arrow. There we go. Get them in there right. So sorry. Okay, with that correction, are we okay? Thank you, thank you. Appreciate it. Now are we good with 21 and 22? Oh, good. So sorry. Okay. We talked about the place value though, right? What place value are we in? Well, if we're on the far right, we're in the ones place. And if we move to the left, we move into the 60s place. So everything on the left-hand side of my vertical bar is the ones place, and everything on this one on the right-hand side, because there's only 2 spaces, is worth 60. And we're literally just multiplying. 21 times 60, 22 times 1, and adding. So I end up having this, and you want your calculator, right? So grab a calculator. 21 times 60 plus 22. What is my grand total? 1,282. Yes?
I got a little lost. So why on the second half are you multiplying by 1 and not 60?
Because we have the base value system, just like ours. Our system is we have, the ones place, and then we have the tens place, and then we have a hundreds place like this. Yeah. They have the ones place, and then the 60s place, and then the 60 squareds place.
Oh, okay.
Yes. Okay, Jeremiah? It's their place value system. That part I had right over here. So in their system, they have a base 60 system. We have base 10, 10 fingers. They used base 60. Okay? So they've got ones, and then they've got 60, and then 60 squared, and then 60 cubed. That's always going to be powers of 60. Okay, 1,282. Let's count the next one. Before my vertical bar, this first piece, how much is this one? 43. So we count 43? Okay, so I have 43. How about in between my vertical bars? 21. And then after the vertical bar, that one's 11. Okay, but again, we're in the ones place on the far right, 60's in the middle, and then the far left this time is 60 squared. So you're going to grab a calculator and you're going to take 43 times 60 squared, or you can do 60 times 60. 21 times the 60, and then 11 or 11 times 1 if you prefer. Did anybody get a value for that? What do you have, Gabriel?
152. 6,071.
That? That's what I have. Is that okay? Okay, so it's important to write this down. When we're going from Babylonian into our system, we're always multiplying. This is always a multiplication step, okay? You see multiplication in these calculations, right? So if we go from Babylonian into Hindu, our system, and we multiply, what do you think is going to happen when we go from our system into their system? We're going to divide. And your calculator is going to be even more important. Now, we already wrote down that this is the base 60 system. We've talked about it a couple different times. There's the ones place, the 60s place. And the next one's 60 squared. And then we have 60 cubed. And that's all well and good, but it'd be actually much nicer for what we're about to do to know what those values are. So somebody tell me, what is 60 squared? What's that? That one's too big. What is it? 3,600. So the ones place, I have the 60s place, I have the 3,600s place. What happens when I do 60 cubed? How much? 216,000. I won't put a comma in it because I'm using the commas to separate the values that I've separated. So I've got the 216,000s, 3,600, 60, and 1. Here's what matters. I need to take whatever number I'm working with. In this case, the number 3 is 3280, right? 3,280. And I need to divide it by the biggest one of those values that it will still go into. So what is the biggest one of those values it will still go into? Actually just 60, right? It won't even go into the 3,600. So the biggest thing I can divide it by is 60, and we're going to do our division so that it looks like this. Now this is probably what you're used to seeing from elementary school. We're going to finish this out like it looks like a top hat, and it has a break over here. And you're going to grab your calculator, and you're going to ask your calculator, what is 3,280 divided by 60? And I want to know the whole number part. It's going to have some decimals, and I want the decimals. I just need to know the whole number part. How many whole numbers do I have? What is it? 54. And we're going to write the 54 over here on the right. And then we're going to multiply that 54 times by the 60. So what's 54 times 60?
3240.
30 what?
3240.
3240. Thank you, Shelby. Okay, so 3240. And I'm going to subtract. What's 3280 minus 3240? 40. Okay, so looks so good so far? And then we go down in place value. Well, after the 60s place, moving down the line, we have the ones place. And how many ones are there in 40? 40, right? And if we multiply the 40 over there by the 1 over here, I get 40, and I subtract. This is just long division. We're just doing it with bigger numbers than you're used to doing it with. And your calculator is a support. Now, the answer is 54 and 40. Those are the answer pieces, but we need to write them in Babylonian. So how do I write 54 in Babylonian? 5 arrows and 4 triangles. That's 54. And then right after that, I need to write the number 40. How do I write 40 in Babylonian? 4 arrows. Okay, let me run through number 4 with you, so it'll finish up our Babylonians real quick. This is 43,205. This time it actually will divide by the 3,600, right? So if I do this in the calculator, your calculator is going to tell you a 12 right here. And if I multiply 12 by 3,600, I'm going to get 43,200, which gives me a remainder of 5. Now, if I'm going down in place value, I need to divide by 60 next, even though I understand that 60 does not go into 5, which represents a 0 over here. And then I will divide by my 1 to get my 5. How do I write a 12 in Babylonian? Arrow, 2 triangles. How to write a 0? I don't. I could leave some space there, but how would I know how much space? So I sort of ignore it. And then how do I write a 5? 5 triangles. This is the number that represents 43,205. Unfortunately, what else does this number represent? How about 17? Does it represent 17?
Yeah.
Okay, so if you're a bookkeeper and somebody owes you 43,205, whatever their units of dollars were, and they pay you 17, this is going to be a problem, right? This is not good. It's not good. And not only is it not good because of the 0, but it's also not so good because we ran the 5s into the 2 that were next to them, didn't we? And even if you say, well, we could have stacked the 5s, that's how we could have distinguished them. But what if it wasn't 5 at the end? What if it was just 2 at the end? Fraught with problems, right? Lots of them. Okay, so I'm going to stop this video. I'm going to post for you the video for the rest of 4.2 for the Mayans. It's probably 15 minutes, okay? Maybe 20. And then this will conclude the section for Babylonians and Mayans, along with what we did from the other section for the homework that's going to be in my math lab. All right?